Swayam Prabha. Digital India. Educated India.
So the next thing that I want to show is a proof that 3-set reduces to clique. Right. So 3-set we have seen it is a class of all Boolean formula which are in 3CNF form and are satisfiable. Right. So something like this. X1, X2, X3, something like 3CNF means this. You have AND of clauses where each clause is an OR of literals, right? So 3-set means it's a 3CNF formula that is satisfiable. Clique means it's a graph, right? So I'll just draw something. So clique is a graph that whose all the edges are adjacent. So for instance, in this graph, the graph that I am just drawing in the corner here, there is a 4 clique. Right? So these 4 vertices constitute a 4 clique, because if you take these circled vertices, you take any pair of them, they are adjacent. This and this is adjacent, this and this, if any pair is adjacent, right? So there are 6 possible, 1, 2, 3, 4, 5, 6 possible edges are there, and all 6 exist, right? So which means this graph has a 4 clique, but it does not have a 5 clique. There are no set of 5 vertices that are adjacent to each other like this. So the clique consists of a pair G and K, where G is an undirected graph with a K clique, right? So if this graph that we have drawn over here is given with the number 4, it will be a yes instance with K equal to 4. But if it is given with the number 5, it will be a no instance, because there is no clique of size 5. If it is given with the number 3, again it is a yes instance, because you could take these 3 vertices and that is a 3 clique, right? So that is the problem of clique. So given in a graph G and a number K, you are asking whether there is a K clique, right? And 3-set I have already mentioned. So it may be a bit surprising that one of them is a problem on Boolean formulas and satisfiability. The other one is something about graphs and having some number of vertices that are adjacent to each other. How is it possible that you can transform one to other, right? So that may seem very surprising. So it's not that hard. So we'll see the reduction in maybe another next 15 minutes, right? So before that, we'll just set up some basic notation. So let n be the number of variables of the, so what do we have to do? We have to, given a 3-set instance, we have to obtain a clique instance. So if the given 3-set instance is satisfiable, then the output clique instance should be a yes instance. If the given 3-set instance is not satisfiable, the output clique instance should not be a yes instance. So it should be a pair G and K where G does not have a K clique, right? So how can we do this, right? So suppose we say that n is the number of variables of the given formula and m is the number of clauses. So remember, the Boolean formula is in 3CNF form, where we have clauses, we have AND of clauses, where each clause is an OR of literals, right? And further, each clause is an OR of 3 literals, right? So you will have A1, B1, A1 or B1 or C1 and A2 or B2 or C2 and something. Finally, AM, BM, CM, right? So this is how the formula will look like, where each of A1, B1, C1 may be X1 complement, X2 complement, X3 complement, anything, right? So that, or XJ complement in general, right? So given this, we need to construct an output something of the form GK such that this formula is satisfiable if and only if this GK is a yes instance of clique, or in other words, G has a K clique, right? So it's easiest to explain this reduction through an example, right? And since I want to draw the picture and explain this example, I am going to resort to a very simplistic kind of formula, but it should be very easy to see how we can deal with a bigger formula as well, right? Just that the figure will get much more messier, but just for understanding for the purpose of understanding this reduction, the example that we are taking is representative enough. Okay, so suppose phi is this formula: x1 or x2 or x2 and x1 complement or x2 complement or x2 complement and x1 complement or x2 or x2. So we have only two variables, x1 and x2, and we have only three clauses. So n is 2, m is 3. Okay, so and each clause, and this is a property of 3 set, every clause has 3 literals, right? So given this, our goal is to produce G and M such that this is satisfiable if and only if G has a M clique, right? So let's see how it happens, right? So first, the graph G looks like this, right? So what do we have here? So we have 3 groups of vertices. So the group by group, this is group 1, this is group 2, and this is group 3. And each group has 3 vertices each, right? So basically we have 3 groups of vertices because we have 3 clauses in the formula. So here we have 3 clauses. So the clause 1 corresponds to this group, clause 2 corresponds to this group, and clause 3 corresponds to this group. So the graph will have 3 m vertices, basically m groups of vertices, and each group contains 3 vertices. So the graph will have 3 m vertices, right? So here m is also 3, so it's 9 vertices here, right? So it has 3 m vertices where m is the number of clauses, and each clause corresponds to a group of 3 vertices, which I have indicated here. This vertex corresponds to clause 1, clause 1, clause 2, clause 3, right? So that is the vertices, right? And it's also labeled as such, right? So this is clause 1 is x1 or x2 or x2. So this is x1, x2, x2. Clause 2 is x1 complement, x2 complement, x2 complement, x1 complement, x2 complement, x2 complement, right? So similarly for clause 3. So I have told the edges. Now I have told the vertices. Now how do we define the edges? So edges are very simple. We want to connect all possible vertices, but with 2 exceptions. We don't connect 2 vertices if one of the 2 cases apply. So one is that within a group we do not have any internal edges. So we don't have edges like this, right? So that is, in that case we do not put an edge. So if you see, all the edges are across groups, nothing within the group. That is case 1. Second is that we do not have edges from x1 to x1 complement, right, and x2 to x2 complement. So basically for any variable I, xi, we do not have edges from xi to xi complement. In other words, so x1 and x1 complement are directly conflicting variable literals, right? X1 and x1 complement cannot both be true. So corresponding to that, I don't want to put an edge between these conflicting things. So for any I, xi and xi complement cannot be adjacent. So here x1 and x1 complement cannot be adjacent, x2 and x2 complement cannot be adjacent, x2 and x2 complement cannot be adjacent, x1 x1 complement cannot be adjacent, right? So for any I, but x1 and x2 complement can have an edge, no problem, because there is no issue with that. x2 and x1 complement can also have an edge, but for the same I, xi complement cannot have an edge, right? So this is the same thing that I said here. We add edges between any 2 vertices except when they are from the same clause and they are labeled xi and xi complement for the same I. When they are labeled xi and xi complement for the same I, and everything else is here. You can just have a look, everything else is here, right? And it should be evident that the construction is straightforward, right? So I have 3m vertices, and I connect them by just doing this. So I have these groups, so I can have a for loop, and then and which outputs the edges, right? Which output the adjacency matrix or something of the graph, right? And we can have maybe at most 3m squared edges, right? 3m whole squared, so 9m squared edges, right? So the construction is straightforward. The running time of this construction is order m square, right? Where order m square is the size of the output, and that's pretty much the running time. The running time is not significantly more, right? So we have, so like in any reduction, we have to show two things. One is that given the instance, so given the three, so in this case, given the 3-side instance, we have to produce a click instance in polynomial time. So that is already shown because I said the construction is straightforward, and I explained the construction. Right, so we can easily produce given the formula, we can produce the graph. Now the second thing to show is that this thing, that any member from A goes to a S instance of B. Anything from A complement goes to B complement, or in our case, any formula that is satisfiable gives us a gk where G has a k clique. Any formula that is not satisfiable gives us a gk where G does not have a k clique, right? So if phi is satisfiable, we get gk where G with a k clique. If phi is not satisfiable, we get gk where G does not have a k clique. This is the thing that we need to show, right? So phi is satisfiable if and only if G has a k clique. So our k is also going to be m, right? So our k is also going to be m. So this is our claim. Phi is in 3 set if and only if G comma m is in clique. Right? So whenever phi is in 3 set, G will have an m clique. Whenever phi is not satisfiable, G will not have an m clique. So that is the claim. Let's see why this is true, right? So suppose phi is in 3 set, right? So this formula is in 3 set actually, right? Because it's a very simple formula. By making x1 true, you can make the first clause satisfied, and by making x2 false, you have to make x2 true to make the first and third clause satisfied, and you can make x1 false. So this is satisfiable, right? So x1 equal to false and x2 equal to true is a satisfying assignment. So x2 equal to true satisfies the first and third clauses. X1 equal to false satisfies the second clause, right? So so we have to show that phi is in 3 set if and only if G has an m clique. So let us assume that phi is in 3 set and then show that G has an m clique. Later we will show the reverse direction. So phi is in 3 set implies that there is an assignment which sets each clause to true, right? Which means every clause has one true literal, and so let's see here. So here every clause has one true literal. So here for this satisfying assignment, right, x2 is a true literal in the first clause, x1 complement is a true literal in the second clause, and let's say x2 is a true literal in the third clause, right? So the highlighted ones are the true literals, right? And what we do is choose the same literals from the graph, right? So here we choose x2 from the first clause, x1 complement from the second clause, and x2 from the third clause, right? So these are the true literals, and the claim is that these three will be adjacent. Why is that? So in the figure you can see that they are indeed adjacent, but why are they adjacent in general? They are adjacent in general because first of all they are in 3 clauses, so they are not in the same group, so that condition does not So we do not put edges only if two conditions are satisfied, or only for two reasons. One is if they are in the same group, and two is if they are of the form x1 and x1 complement, or x2 or x2 complement, and so on, right? So none of them are in the same group because we picked each one from a different clause. So the only way there will not be an edge between two of these. The only way there can be an absence of an edge between two of these is if they are of the form xi and xi complement, right? But then we cannot have xi and xi complement because we picked true literals from each clause. So if our assignment xi was true, then xi will be the true literal, xi complement will not be the true literal. So hence, if we picked x2 here, x2 complement will not be true, right? So we cannot pick xi and xi complement from two different clauses. So hence, so that is the other way in which there may not be an edge, right? So there will be an edge between any pair of vertices here, because firstly they are all from separate groups, and secondly we do not have any pair xi and xi complement, because if it was there, then it will be a contradiction to the way we chose these variables, right? So these literals were chosen such that they are all true. So if xi is true, xi complement cannot be true. If xi complement is true, then xi cannot be true, right? So both of them will not be true together. So either for a variable xi, the xi was a true variable and only xi was picked, or xi complement was picked, but not both. So that means that the vertices picked from the three groups, or from the m groups in general, right? So in general we have m clauses, all of them will be adjacent to each other, and that gives an m clique. And here we have a 3 clique because m is 3, right? Same thing here. So every clause has at least one true literal, and so we choose one true literal from each clause, and these correspond to m vertices because they are m clauses, and these m vertices will be adjacent because we cannot have both xi and xi complement set to true, right? This is a key thing, we cannot have both xi and xi complement set to true. Hence the graph has an m clique, right? Now the reverse direction, suppose the graph has an m clique, then we have to show that the formula is satisfiable, right? So suppose the graph has an m clique. Now we know that there are m groups, right? And we know that we do not have any edges within the same group. These edges do not exist. So which means I can have at most one vertex in this m clique from each group. I cannot have more than one vertex, because if I pick two of these vertices, then this is not going to be a clique, right? So I can have at most one vertex from each group, but then there are only m groups, which means I have to have one vertex from each group. So if this graph has a 3 clique, then it has to be one vertex from each of these 3 groups, right? Because inside I am not putting internal edges, so we cannot have 2 from one group, so it has to be distributed 1 1 1 1, right? So G has an m clique means that each vertex in the clique comes from a distinct group, which means each group contributes exactly one vertex, right? So the clique contains exactly one vertex from each clause, and we know that we cannot have xi and xi complement in the clique, because if I picked for some I xi and xi complement from two separate groups, we know there is no edge between them. That is the rule that we have. So if for any variable we picked xi, then xi complement was not picked. If for any variable we picked xi complement, then xi was not picked, right? So because we didn't put edges between them. So what we have is some set of m literals. So these m vertices that form a clique correspond to some set of m non-contradicting literals, right? So here, if you look at the clique, so maybe another clique that we can identify is this one. But in this case, there is only one satisfying assignment. So all the cliques that you identify will be of the form x1 complement x2 x2, right? Because that is the only satisfying assignment. So x1 complement x2 x2. So the thing is that we don't have x1 and x1 complement, we only have one of them, and same we don't have both x2 and x2 complement, we only have one of them in the clique. So for some variables, for some xi we have xi, for some xi we have xi complement, right? So so we have some, let's say for x1 is picked, for x2 is picked, for x3 let's say xi complement is picked. Now what we do is we set all these to be true. So if xi is picked, we make xi to be true. If xi complement is picked, we make xi complement to be true. In other words, we make xi to be false, right? So we make all the selected literals to be true. And this will be completely fine because we do not have conflicting literals. If xi was set to true, xi complement will never have been set to true, because these two cannot be part of the same clique. So we assign true to all the m non-contradicting literals, and by choice by the choice of the literals we picked exactly one true literal from each clause, or we picked the clique contained one vertex from each clause which we set to true. So we have one true literal from each clause, so each clause is satisfied, right? And since each clause is satisfied, that means that the formula is in 3 set. There is a small point. So it is possible that since we assigned some xi to be true, some xi to be false, it is possible that some xj's or some xk's may not have been assigned anything. Maybe the same, let's say x1 may satisfy 2 clauses, x2 may satisfy 3 clauses. So maybe it so happens that x4 is never assigned by this process. But what it means is that we can assign x4 to true or false, it doesn't matter. Whatever we assign, we have already satisfied all the clauses, right? So in any clause that contains x4, there is some other variable that has satisfied that clause. So whatever we assign x4, it doesn't matter, right? So the unassigned variable, we assign anything, it doesn't really matter. But the point is that by the virtue of assigning these literals that were chosen from the clique, we had satisfied all the clauses, and hence the formula is satisfiable, right? So let me just recap. We have to show that formula is satisfiable if and only if the constructed graph has an M clique. If the formula is satisfiable, we pick at least one, we consider satisfying assignment, and we pick one variable or one literal from each clause that is satisfied. And the claim is that these form a clique, these form an M clique, because they are from M clauses, and because it's a satisfying assignment, it will not have both xi and xi complement for any I, right? The other direction, so this forms a K clique, M clique. So if G is if phi is satisfiable, G has an M clique. For the other direction, if G has an M clique, we know that each group or each clause has only one vertex, cannot have more than one vertex because there are no internal edges. So which means each group has exactly one vertex, right? And now we just select those groups, and because we did not put edges between xi and xi complement, we know that all these selected literals or all these selected vertices or the literals that correspond to these vertices, they are not conflicting, and we can set all of them to be true. So suppose x1, x2, x3 complement, x4 complement are picked, then we set x1 and x2 to be true and x3 and x4 to be false. So now that translates to at least one satisfying literal in each clause. So each clause is satisfied, hence the formula is satisfied. So there may be variables that we do not set either way, but we can set in any way, it doesn't matter, right? So that completes the reduction and the proof of correctness of this reduction. So the reduction is straightforward, the proof of correctness is a bit more involved. So we saw that given a 3 set instance phi, we can construct a graph and M such that phi is in 3 set if and only if G has an M clique, right? And prior to that, we defined polynomial time reductions, right? So it's a transformation from an A instance to a B instance such that every S instance is mapped to a S instance and every no instance is mapped to a no instance. And further, the computation of this reduction function should be in polynomial time, right? So we had all these results. A reduces to B and B is in P implies A is in P. A reduces to B and A not in P implies B not in P, and all of this, right? And finally, that kind of concludes the lecture 48. And I just want to make one small remark before concluding. So the construction that we had for showing that satisfiability reduces to clique. So there is a certain pattern or structure to this, right? So whenever we are reducing, or many times when we are reducing one problem to another, sometimes we need to make use of some of these types of constructions, and these constructions are like commonly called as gadgets, right? So these tools for making the reduction, right? So sometimes they are called gadgets, right? So this is just to familiarize with the term, right? We will not be seeing that many reductions in this course, maybe like 4 or 5 reductions maybe in the next week. But if you look at a book on reductions, and if it uses the word gadgets, I'm just saying this so that you can be familiar with this usage, right? So that's it. So we saw reductions, we saw the definition, we saw one example that 3 set reduces to clique, right? And that's all for lecture number 48. And next we will see NP completeness in the coming lectures. So see you in lecture 49. Thank you.